Let's take a look at section 15.3, which is going to expand our double integrals into generalized regions instead of just rectangles. So just one learning objective this time, and that'll be to calculate those double integrals over generalized regions. So let's take a look at a couple kinds of regions, because since now we're going to be opening ourselves up to look at any sort of region, we're going to start by maybe breaking down those general regions into some things that are slightly more easy to talk about. So instead of jumping right into totally random regions, we want to kind of have a one bridge step in between rectangles and something crazy. So we're going to call these two new types of regions, type 1 and type 2. The type 1 and type 2 names aren't overly important, but being able to kind of recognize what they look like and what it should mean is going to end up being important. So let's go with definition of a type 1 region, which type 1 region is anything up similar to something at the top, and it's bounded on top and bottom by functions of x. So plane region, said to be type 1, lies between graphs of two continuous functions of x. In other words, it fits that fancy inequality where y is stuck in between two functions, g1 and g2. And what you might want to think here is that a type 1 region is one that can pass the vertical line test. The vertical line test. And that means that the top and the bottom should pass that vertical line test. So if we pull out the ruler here and look at, any vertical line through these regions, we can see that the functions along the top and the bottom are going to pass that vertical line test. Meaning that, just the standard vertical line test that we have back in Calc 1, or actually not even Calc 1, that's algebra. So it's a function if a vertical line will only hit the function in at most one spot. And we're looking at both a top function and a bottom function, which means that they'll both individually pass the vertical line test. Since, as you can see, each of those vertical lines is intersect the regions in a whole bunch of places, but I just want to look at the boundaries and look at two separate boundaries, so I'm really looking at the vertical line test twice. A region then is type 2 if it does kind of the conjugate of that. So instead of lying between functions of x on top and bottom, I want to lie between functions of y on left and right. So if the top were the vertical line test, a type 2 passes a vertical line test, we'll want a type 2 to pass a horizontal line test. And I might have just said that backwards. Type 1 should pass vertical line test. Type 2 passes the horizontal line test. So if we pull our ruler back out, this time set it to 0 degrees and look at some horizontal lines, we can see that the two figures to the right would both be type 2, and they can pass a horizontal line test for both the left and the right boundary. And our strategy for integrating these two types of regions will end up being just a little bit different. Also worth noting, just because a region is type 1 does not mean it cannot be type 2. So for example, if we look at, how about we put stars by the regions that are both? Those two at least are both going to be type 1 and type 2, since I could pass a vertical line test down either of those. But we're getting slightly ahead of ourselves. And also we might have to split those regions into saying that they're both type 1 and type 2. So maybe let's erase those stars for now. But we will look at some regions that are both type 1 and type 2. So let's talk specifically about how to integrate over a type 1 region. So if we have a continuous function on a type 1 region, again, meaning that our region is stuck between a function of x on top and a function of x on the bottom, then we can say that the double integral is equal to a rather nice looking iterated integral, where in a type 1 region, we want to express everything in terms of x, which means that we're going to take an integral of y first, and our bounds will be two functions of x, and then move into doing the second integral in terms of x. What that looks like is if I've got my region D down below, and I've got this magenta rectangle that I'm passing through the region, the volume over the region that's above that rectangle is equal to the integral with respect to y, so that interior integral where we integrate between the two functions of x. So we're going to have some volume that lies above that rectangle, and then we're going to shift that rectangle over all x between a and b. And we say volume, it's kind of actually closer to an area. So the width of that rectangle is going to be dx. So if we actually break down the volume of that rectangle, it's going to work out to some area where the area has a height that is the height of that pink rectangle, but the length comes up and out of the page because it's going to go up in the z direction to reach the top of whatever function we're integrating. So we're going to have that area. So it's not the area that we're sort of looking at, where we should just be looking at a vertical line with an area that then comes out of the page, and then it has a width of dx. So we've exaggerated the width of that magenta rectangle for the sake of this example. But when we say it's a volume, it's really going to be an area times dx. And it'll end up looking more like a thin line that we pass through all those x values from a to b. So let's put that into practice, evaluating a double integral over the region that is bounded by parabolas 2x squared and y equals 1 plus x squared. So we've mapped that out in figure 8, where 2x squared is going to lie on the bottom and 1 plus x squared will be on the top, and then we would set those two equal to each other to find their intersection points. But we can see from the graph that intersection is at 1, 2, and negative 1, 2. So if we set up the integral that we'd like to do, we're going to be integrating our x values from negative 1 to 1. And we'll need bounds for our y, which will be the top and the bottom functions of x. So the bottom function was 2x squared, and the top function 1 plus x squared. Fill in the integrand, which is x plus 2y, and we're doing this in order of dy first and dx second. All right, with all that out of the way, let's go ahead and take ourselves an integral, or actually a series of integrals. So let's make that mark a little bit bigger so it doesn't look like a stray negative sign. So we're still going to be integrating from negative 1 to 1. So we don't need to take that part out just yet. But we're not going to worry about it, as first we'd like to deal with the y partial, what's that going to come out to? Looks like we'll have xy plus y squared. And we'll evaluate it from 2x squared. 2x squared, we'll stick to the same color scheme we started with, up to 1 plus x squared. And then finish that off with a dx. So if we evaluate that mess, what will we have? We'll start by plugging 1 plus x squared in for y. So x times 1 plus y squared plus, now we get 1 plus y squared squared. And subtract from that what we get when we plug in 2x squared. Ooh, I wrote y squared twice. That was not what we wanted. We were plugging in for y. That should have been 1 plus x squared and 1 plus x squared. There we go. Minus the stuff we get when we plug in 2x squared. So that'll be x times 2x squared minus 2x squared. In turn squared, close all of that parentheses and start filling in the leftover pieces. There's a dx on the outside. We go from -1 to 1. Maybe let's move that in just a little bit. Cool. All right, now we're going to want to simplify everything that we just wrote down. Okay, so we're going to have all kinds of terms from x to the 4th all the way down to a constant term. So let's get cracking. So if we follow our x to the 4th terms, looks like we'll have a 1x to the 4th from the second green term and a minus 4x to the 4th from the second blue term. So we'll call that -3x to the 4th. If we have any x cubed terms, we'll get those out of the way next. It looks like we have 1 from the first green term plus x cubed. Let's gather up our x squareds next. We'll have a, oh wait, slow down. We missed one, or rather I missed one. So we have a plus 1x cubed from the first green term, but we also have a minus 2x cubed from the first blue term. So x cubed minus 2x cubed will be minus x cubed. There we are. All right, now let's gather up our x squared terms. I believe we'll only have 1x squared, and it will show up from the second green term when we square all that out. Should be plus 2x squared. Then we'll follow along for any single x terms. I believe there's just the 1 that we get from the first green term, which should be plus x. And finally, a constant term. We'll have plus 1 from that second green term as well. Said term too many times. It's starting to sound weird. And cool. Do all that integration. So let's evaluate this last piece. So we're integrating from -1 to 1. So we can kind of help ourselves out with some even and odd terms. Any odd term that we integrate is going to integrate to 0 if we integrate from -1 to 1. And any even term will integrate to 2 times its just plugging in the top number. So it'll be 2 times the integral from 0 to 1. So it looks like we'll need to have a little bit more space. So let's move that over here. So this will be equal to since again we're doing an odd term or even terms, 2 times the integral from -1 to 1 of whoops. We're just gathering up our even terms here. -3x to the 4th plus 2x squared plus 1 dx. And then plus 0 for all of our odd terms, since they would again integrate to 0 if I integrate from -1 to 1. Oh, and we're not doing -1 to 1 anymore, are we? We're doing 0 to 1, since we're doing the even terms. So taking this integration doesn't look too bad. We'll have -x to the 4th. Well, let's try that again, because that's not how numbers work. -3 over 5 x to the 5th. There we go. Plus 2/3 x cubed plus x. And we'll evaluate from 0 to 1 and multiply everything by 2. So in the end, what do we get? -3/5 plus 2/3 plus 1, and then all of that times 2. So 2 times -3/5 plus 2/3 plus 1. And what does that come out to? That'll be -9/15 plus 10/15. So that's just 1/15 plus 1 is 16 over 15. And multiply all that by 2 means we have 32 over 15. Really hope my math worked out right there. No. There we go. All right. Then let's try this again, but this time we'll look at integrating over type 2 regions, where a type 2 region should look pretty similar to a type 1, except we're going to do functions of y instead of functions of x. So we're going to have a right and a left bound instead of a top and a bottom bound. And we're going to integrate x first, since our goal with the type 2 region is to get everything in terms of y. So x is first, we integrate between two functions of y, and then in the end we'll have one function of y that we're integrating. Where just like we looked at with the x integral, this time we're going to have a volume of the region that's over that magenta rectangle, and its integral. It's equal to the integral of the function with respect to x between two bounds of y. And then we're going to shift the rectangle from bottom to top, covering all y values from c to d. And again, the width of, or maybe this time it's the height of this rectangle, is going to be dy. And the volume of that region that we're talking about, it has this time it's got a width that is the width of that magenta rectangle, and again a length that's going to come out of the page, so it's going to go into that z direction. So the volume that we mean when we're talking about all of this, I think we had volume in magenta because it's going to be the volume over that magenta region. It's equal to the area that comes out of the page and then multiplied by dy. So the height of that rectangle has been exaggerated for the sake of example, because really the height of that rectangular region, I keep saying rectangle, but it's really a rectangular region, and its height is equal to dy. So just an infinitesimal length in the y direction, which means it actually looks, I think it shares more properties with an area than it does with a volume, and then it's going to only gain volume as we pass it over all possible y values between C and D. But let's apply that to an example. This time we're going to evaluate the function 3y over the double integral of 3y over the region bounded by the square root of 1 minus y squared and the negative square root of 1 minus y squared. So hopefully you recognize that as a circle of radius 1, just to split into two functions of y. So we have a right function and we have a left function. On the right, we have x equals the positive square root of 1 minus y squared, and on the left, we'll have x equals negative the square root of 1 minus y squared. So if we throw all that into an iterated integral, we're going to kind of break the pattern that we had going, and we're going to use magenta for the y bounds this time. Y is going to go from -1 to 1, while the x goes from the left function of y to the right function of y. And on the inside, we're just integrating 3y. Now we'll want to do this in the correct order. We have to do x first. So first it'll be dx, and then we'll do y second, dy. All right, let's give this thing a shot. At least that x integral comes out to be pretty nice. We will just have the integral from -1 to 1 of 3xy. Well, let's just write it 3y times x. And we evaluate that thing from the negative square root up to the positive square root. And then we'll go ahead and put our dy on at the end as well. So if we evaluate that integral, just plug in the square root, the positive square root, then minus the negative square root should come out to 2 times that square root. So we also could have done what could we have done? It looks pretty similar to an even integral like we had in the last example, but this time they're two even functions from top to bottom rather than the same number. But right, we had 6y times the square root of 1 minus y squared. And dy should go on in there. And it'll probably help to make a u substitution here. Let's see, what color have we not used? We haven't used orange yet. Or maybe that's yellow. Yeah, either way. We'll make the u substitution that u is going to be 1 minus y squared. So du is negative 2y dy. So if we reorganize that integral, we'll be doing 3 times the integral of, let's actually call that -3, because we're going to need a negative to come out of here as well. So -3 times the square root of u times du. It looks like we might want to give ourselves a bit more space for this example as well. So putting all that together, we'll have -3 times, if we integrate u to the 1/2, we'll get u to the 3/2 divided by 3/2. So times 2/3. And let's go ahead and plug in what we know for u again, which is 1 minus y squared. And now that we've changed back to y, we'll continue to evaluate this thing along the values of y we were given. So -1 to 1. And if we plug in 1, we'll get 1 minus 1 squared, which is 0. And if we plug in -1, we'll get 1 minus -1 squared, which is also 0. So ultimately, this thing is 0 minus 0, which is 0. Cool. Alternatively, we could have noticed that the square root of 1 minus y squared is an even function being multiplied into 6y, which is an odd function. So altogether, we're integrating an odd function from -1 to 1. And the value of an odd function integrated from -a to +a, whatever that constant a might be, is going to come out to 0. So we could have used even and odd properties again, had we wanted to. But let's go look at some other properties of integrals over regions. So the first one that we're going to look at says that if we have a couple of functions f and g that are continuous on the bounded region D, and D can be split up into the union of two individual regions, then we can split up our double integral into the sum of integrals over those two smaller regions. Let's take an example. Look at an example of what we mean by that. So figure 18, we're starting with that sort of wackadoodle amorphous blob D that doesn't really fit into any nice kind of integration that we would want to do. But if we choose instead to split the region, like in the figure on the right, we can split it up into a region D1 and a region D2, where D1 is a type 1 region and D2 is a type 2 region, meaning that those two smaller regions, D1 and D2, are going to be much easier to do an iterated integral over. So that first theorem just said if we have some crazy region, then probably our best bet is going to be to start splitting it up into smaller regions where an iterated integral will be much easier. So that's the first theorem. Looked and sounded complicated, but I think if you look at the pictures, it makes quite a bit more sense. The other two properties we'll look at are mostly just some sanity check type stuff. If we just integrate 1 times, or do the double integral of 1 times dA, it'll give us the area of the region. And so basically, just integrate dA and you get the area. And the second thing is that if we know that f is bounded by a couple of constants, so a small constant on the bottom side, a large constant on the top side, then we could say that that double integral is going to be greater than or equal to the smaller bound times the area and less than or equal to the larger bound times the area. Mostly that can just be used to check an answer by the time you get all done. If you get an answer and you're not sure if it makes sense, you could find some easy upper bound and lower bound and just check it against the area of the region you were working with. And as long as your answer lies in between those two values, the area multiplied by either the lower bound or the upper bound, then you at least know that your answer has a higher possibility of being correct. Whereas if you got an answer that was outside of those two numbers, you know for sure that some kind of crazy mistake has happened. You might want to check your work again. But let's get into the real fun stuff, switching bounds. So we talked about that in the last section, and we're probably going to want to apply it in this section. So the problem that we might run into. We have a nice looking region, cool. It happens to be a type 2 region that we're looking at and a type 1. But we've set it up for a type 2 region style integral where we're going to put everything in terms of y. So it means we're doing the x integral first. But if we do the very first step, which is to integrate sine x over x dx. We have a bit of a problem. Since no amount of u substitution is going to help us out here, we just don't have an antiderivative for sine x over x. So we don't really know what that thing should integrate to. And again, the thing I pointed out was right here, no antiderivative. At least not one that we know already. Which means that trying the integral this way is going to be rather complicated. So instead, what we're going to want to do is just change the bounds for this integration. So instead of doing an x and then a y integral, we'll want to see what happens if we rewrite everything and try to do y first instead of x. So what we're going to want to do is start by looking at the first integral that we would have to do and looking at the bounds, which are y and x. We're doing an x integral first, which means we have the boundary equations x equals 1 and x equals y. Since again, we're doing the x integral first, it should be x equals each of those bounds, which gives us a couple of equations that we can plot, which I've done below over that purple region, which probably would be D, but we haven't given it a particular name yet this time. So we've put our two boundary equations down. We also see that y is going to integrate from 0 to 1, so it must be this triangular region. We have a right bound and a left bound. Right bound is the one that was on the top of the integral, the left bound is the one on the bottom of the integral. And what I want to do is change this thing so that we do a y integral first and then an x integral, so changing from a type 2 to a type 1 region. So instead of having a left and a right bound, I want a top and a bottom bound. And looking at this triangle, the top bound is going to be that green line, and the bottom bound will be this blue line. So we'll just rewrite each of those equations so that they're a function of x instead of a function of y, and both of them don't look so bad. That green region is just going to be y equals x, right? Just take the equation that we had before and solve it for x instead of for y. This one was not very complicated since it's the same on both sides. Then we also need that bottom region, which is going to be y equals 0. So we'll just reorganize our, reorganizing our integral, or our double integral, I should say, so that we're going to do everything in terms of x. We needed a bottom equation for x, which is 0, and a top equation for x, which is just y equals x. I guess that's a bottom equation for y and a top equation for y, because the first one is now going to want to be a y integral. We don't change anything on the inside. That should still be sine x over x. We're doing dy first and dx second. We've changed things around, and I don't want to use magenta again, so let's just switch to purple. So we'll have dx. Where we'll need to find bounds now for x. So a left bound and a right bound for x, which looks like it's going to be 0 out to 1. Since we look at that line over here, where x equals 1 was our right bound. So integrate x from 0 to 1, but only after we integrate y from 0 to x. Then let's also maybe move that red text out of the way so I have a little bit more space for this integral. Also kind of came up into the border, which is going to make that hard to read. So if we do that first integral with respect to y, We'll leave the x part alone for right now. The inside really isn't so bad. We'll get sine x over x times y, and we evaluate from 0 to x. And then we still have to do the x part after that, split a dx and keep those bounds there. Not super happy with what that y ended up looking like. Okay, so if we plug in 0 and x for y, we'll multiply by x, then multiply by 0, so only one of those terms makes it through. And sine x over x times x will be just sine x. Then we do this integral dx from 0 to 1. And this integration is much easier than the one that we had before. Because the one that we had before, when we had to integrate sine x over x dx, it was not something that we know how to do. But this one is much easier. The integral of sine x is negative cosine. So we'll just go ahead and plug everything in right away, because this one's not too complicated. Negative cosine of 1, if we plug in the upper bound, minus negative cosine of 0, if we plug in the lower bound, and cosine of 0 is 1. So negative cosine of 1 plus 1, or 1 minus cosine of 1, if we wanted to rewrite to have a positive term first. All right. Cool, so let's look at another example where we're going to want to switch the bounds and also move another example out of the way for now. So again, same story. If we look at trying to integrate e to the x to the fourth dx, that'll get kind of complicated. So we don't have a great way of doing that. So instead, we're going to want to switch our boundaries around, just like we did last time. So we'll look at those two equations again, which give us x equal 2 is going to be the right boundary. X equals the cube root of y, or y to the 1/3 will be our left boundary, and sketch the region that it comes up with. So we just draw the cube root equation sideways to get the left bound. The right bound is just vertical lines, so that one's not too bad. And we're going to want to do the same thing we did last time. Rewrite this in terms of a top and a bottom boundary instead of a right and a left boundary. So if we go to take a look at the top, it'll be that green line, whereas the bottom will be this blue line. Bottom's not so bad, it's just y equals 0. For the top boundary, we'll just solve the equation that we had. So x equals y to the 1/3, solve that for y instead of for x. And we should get y equals x cubed. And now that we have those new boundary lines, we'll just change our order of integration. To be the bottom function to the top function, so 0 on the bottom, x cubed on the top. Our interior function doesn't change, e to the x to the fourth, but now we're going to do dy first instead of dx, with dx happening second. And let's find our new bounds for x. So we need a left and a right bound for x, which, if we take a look at it, our left bound is going to be at the origin, so it'll be at 0, 0, and our right bound will be at 2. So notice that the y bound previously, so when we started off our equation, our y bound was 8, and our x bound is 2, and we'll get that if we look at the point that's up here in the upper right. and set the point to 8. So it made sense when we were integrating y second that we'd integrate from the bottom to the top, so from 0 up to 8. But now that we're doing the left bound second, we integrate from left to right, so from 0 out to 2. So that 8 doesn't really play a role anymore now that we've switched to doing x second. But let's do another integration. So we'll integrate e to the x to the 4th dy, which will just be e to the x to the 4th times y, evaluated by our two bounds, 0 on the bottom, x cubed up top. Put in our x bounds, dx 0 and 2. So this thing is just gonna be x cubed times, or well, let's do it this way, e to the x to the 4th times e, nope, try that one more time, times x cubed, dx from 0 to 2. And then this next integration, again, won't be so bad because now we have an x cubed term that we're multiplying in, so u substitution will go pretty well. U can be e to the x to the 4th, meaning, or let's try that one more time. U is going to be x to the 4th. Du will be 4x cubed. So this integral should be 1/4 e to the x to the 4th, evaluated from 0 to 2, which will be, what is that? Well, looking at 1/4 times e to the 16th minus 1/4 times 1. So 1/4 e to the 16th minus 1/4, or e to the 16th minus 1, all over 4. Dealer's choice on that one, I suppose. So let's look at one last thing. So we said earlier that some regions could be type 1 and type 2 at the same time. And here we have an example of that region. So D is a region that can be both type 1 and type 2. But if given our choice of which way we wanted to integrate this thing, type 2 is definitely going to be easier this time. This is the way we want to go, if we can. Sometimes the particular integrand that we have is going to force us into integrating it one way or the other, but if given the choice, we're going to want to choose type 2. Because if we stick with type 2, there is just a single right bound and a single left bound. If we look at this line and this curve right here, meaning if it's type 2, it's quite easy. If we try to do this as a type 1 region, our lower bound is going to change part way through. So if we look at drawing in this red line right where we have the lower intersection point, we'd split this up into one top curve and one bottom curve, here illustrated by green and blue. But then after that, we'd have to split it up into a couple of other curves. Yellow doesn't show up, so let's just do purple and magenta. We'll have this top curve on the right half, but this bottom line on the right half. So trying to do D1 as a type 1 region where we try to express everything in terms of X is going to be considerably more difficult than just expressing it as a type 2 region where we have everything expressed in terms of Y. So again, if given the choice on this particular region, we'd much rather do a type 2 region rather than a type 1 region. But more on that later.